Hi, everybody. So today, I'd like to talk about the ratio and the root test. So these are, again, two tests to see whether an infinite series is convergent or not. And again, like we had before, these don't tell us what the actual value of the series is. It just tells you, is it convergent or is it not convergent? And so that's nice. And the nice thing here is that this one actually does tell us whether it does converge or it doesn't converge. So unlike the divergence test, that one only told us one piece of information. This tells us whether they converge or not. The downside of this is this is only going to catch those that are absolutely convergent, and it's not going to catch those that are conditionally convergent. So those that converge even though their absolute value does not. So the ratio and root test tell us whether a series is absolutely convergent, and so that's nice. So here, let's talk about the tests a little bit. So we talked a little bit about some of these. We want to know how we can check convergence. A lot of them rely on the series having only positive terms or terms that alternate in sign. They also rely on integration a little bit. So for example, this series here, 1 over k factorial. And just to remind you, k factorial, if I say k factorial, this means the product of all of the numbers from k down to 1. So you're multiplying k minus 1, k minus 2, k minus 3, and so on, down to 2 times 1. So the last two terms are 2 times 1. Right? So you're multiplying all those together. That's the factorial. And that's what we're wanting to figure out. Now, the hard thing is that I cannot think of this as like a function. This is not a function of any x value. It's only a function of integers at this point. So this wouldn't make sense to integrate this thing because the integral relies on the fact that you can integrate over a really big interval, like over pi. So pi factorial doesn't make sense. But 15 factorial does make sense. So integers here are the only things I can plug in. So this makes it tricky. So I first off have a series that has negative terms. Every term is negative. So they're not alternating in sign. So maybe it's okay if I take like the absolute value and say, oh, is it convergent? Unfortunately, then I have to rely on an integration, and I cannot integrate the k factorial away without some work. So I actually can't do this without defining factorial in another way. And so this doesn't work out for me. So we have to do something else. And it turns out what we can do here is we can talk about the ratio of two terms in my series, and it'd be like the term and the next term in the series, and that will tell me whether this thing is actually convergent or not. So in particular, the first test we have is this ratio test. I take the absolute value of the ratio of the next term, the k plus 1 term, divided by the k term, and I take the limit as k goes to infinity. If this limit is small, is less than 1, the series converges absolutely, and therefore it means it converges. So absolutely meaning the absolute value of whatever the AK is converges when I add them. So the actual series itself also converges. If R is bigger than 1, this is a divergent series. And if R is equal to 1, this ratio test is inconclusive. So unfortunately here, if we're equal to 1, we say, oh, this test didn't work. We have to do something else and go from there, right? So let's check it out a little bit. So for example, the series that we had before. So I've got 1 over k factorial, negative 1 over k factorial, and I want to figure out whether this converges or not. So I want to apply that ratio test that I just had. So I look back at the ratio test and I say, okay, so I need to take the k plus 1 term, divide by the k term. So let's take the k plus 1 term, and that is just to say negative 1 over k plus 1 factorial. I want to divide that by negative 1 over k factorial. So the k plus 1 term over the k term, I take the absolute value of that. And then I want to do the limit of this thing as k goes to infinity. So I sort of think about this a little bit. I'm dividing a fraction. The minuses cancel, so I just get positives. When I divide a fraction, I flip the bottom fraction and multiply. So I end up with the absolute value of 1 over k plus 1 factorial times k factorial over 1. Right. And that, I just multiply the k factorial on the top, and that gives me k factorial over k plus 1 factorial. And now I have to think a little bit. Okay, so k factorial is just the product, of all the numbers from k down to 1, right? So I have k minus 1, k minus 2, and so on, down to 1. K plus 1 factorial is k plus 1 times all the numbers below it. So that's times k minus 1 times k minus 2, and so on. So really what I'm basically getting here is the top is just k factorial, and the bottom is actually k plus 1 times k factorial. The k factorial will cancel, and I can now reduce this to just 1 over k plus 1. Great. Now, the limit as k goes to infinity of 1 over k plus 1 is 0. And that's the r that we're talking about. And since that r is less than 1, this is a convergent sequence. So this sequence converges by the ratio test. So I take this ratio, I take the limit, it goes to 0, or it goes to something less than 1. We're at a convergent sequence. So I'm able to stop there. All right, so this is great. It does not tell me, however, what I am converging to. And in particular, it's just not going to give me that information. Okay, we can do another one. So this is one that's it's similar to that one we just did, except now I've got 10 to the k plus 1 over k plus 1 factorial. And now I divide that by 10 to the k over k factorial. Again, I multiply by the reciprocal of the denominator. So I get 10 to the k plus 1 over k plus 1 factorial. And I'll play the same game I did before, where I can reduce that k plus 1 factorial, and then I can go from there. Now, the other thing I need to do is I need to maybe group the 10s together as well and think about that. So let's see what we have here. So what we have here, I've got 10 to the k plus 1 over 10 over k plus 1 factorial. That's 10. Now let's do this. So what we end up with is just 10 to the k plus 1 over 10 to the k times k factorial over k plus 1 factorial. To reduce the k factorial, k plus 1 factorial, I can just reduce this, and this is k plus 1 times k factorial. So the k factorials cancel. The 10 to the k plus 1 over 10 to the k, I subtract exponents when I do a same base and divide. So I actually get just 10 to the 1 on the numerator. So what I get here is just 10 over k plus 1. Limit as k goes to infinity of this thing is, again, just 0. And so I'm left with an r that's less than 1, meaning this is a convergent sequence. So this sequence converges. And it converges absolutely, meaning it also converges normally. All right, so we have a convergent sequence. We're pretty happy. For those terms that involve powers with k in the exponent, we have another test that might help. So this one was okay because I was able to sort of cancel 10 to the k out. Sometimes I'm not able to do that. So sometimes I can't actually just cancel the k out. So if I have k to the k power, that's kind of tricky because I can't actually cancel the k with the k plus 1. And so this is going to be a little bit weird. So instead, we have another test. So if you've got k powers, the root test will be able to tell you whether this thing is convergent or not. So you take the kth root of the absolute value of a sub k and take the limit as k goes to infinity. Same sort of deal. If it's small, if this limit is small, if it's less than 1, it's convergent. If it is big, it is divergent. And if it's equal to 1, it's inconclusive. So we don't know if it's equal to 1, we don't know what happens. But if it's big or small, we can tell you what's going on. Same sort of deal. So let's take a look here. So what I'm looking at here is 3 minus 4k squared over 7k squared plus 6 all to the k power. And so you're going to see, like if I tried to do the ratio test, I've got a k plus 1 now throughout all terms here. I've got a k on the bottom throughout all terms here. You're going to have things like k squared to the k and k plus 1 squared to the k plus 1. And so the base does not match. I can't just sort of cancel what I'm trying to do here. So I cannot do the ratio test in this situation very well. But what's great is the root test here works out really nicely. So let's check it out. So what am I going to do? I'm going to take the kth root of 3 minus 4k squared over 7k squared plus 6. And I'm going to do an absolute value on the inside. Right? And that's all to the k power. So with the absolute value there, it actually doesn't matter with the kth power if I have the inside or outside the absolute value there. So think about that a little bit. But basically, the absolute value when I take the kth root of the kth power will just be the absolute value of 3 minus 4k squared over 7k squared plus 6. Okay, so if that ends up being positive, we're okay. If it ends up being negative, you make it positive, because if it was like a square root of a square, you take the absolute value at the end of all of that. All right, so what do I get here? So what I get here is absolute value of 3 minus 4k squared over 7k squared plus 6. And now I take the limit as k goes to infinity of that. And as k goes to infinity, I get negative 4 over 7 in an absolute value, which is positive 4/7. And that is smaller than 1. So since the limit, again, is smaller than 1, so I'm looking back here, the limit is smaller than 1, we have a convergent sequence, and it converges absolutely. So this is telling me this is actually convergent. So this whole sequence here is convergent. Okay. So we're in a convergent sequence. We're happy. We don't have to do any more. And this is unfortunately not going to tell me anything about what the value is. But that is a harder question that we kind of don't answer in this section, at least. So there we go. So let's do another example. So I've got minus 1 to the k to the k over k factorial. Okay. So here I have a couple of options that I might try. But what I would actually mention here is that what we really should do here is think about the tests that we already have. So the divergence test, the convergence test, the integral test, the alternating series test. So let's look at the alternating series test here, because this series is alternating between negatives and positives. And so I think about k to the k over k factorial. Okay. And so we have to remind ourselves which one of these goes to infinity faster, because again, these are both going to infinity. And I suppose I could do some sort of limit, some sort of test here, right? I could do the L'Hopital's rule and try to go from there. But we had a list of these things already. And so we had a list of these things. So I'm going to go dig back in here and I'm going to say, okay, so that we're talking about increasing functions and how fast are they growing. So we're talking growth rates. So growth rate wise, k factorial grows slower than k to the k. So what that means is that the k to the k over k factorial in the limit as k goes to infinity will be infinity. So here, the limit as k goes to infinity of k to the k over k factorial is infinity. This is divergent. So it does not go anywhere nice. It actually goes to infinity as k goes to infinity. And so what we're left with here is actually this is a divergent sequence. I don't have to do any more. And it's good to try to do those tests before you have to do the other tests. I will say you can do this with the root test as well. I just have to know one little fact, and I'm going to give it to you here. The kth root of k factorial as k goes to infinity is just 1. Okay, and you can sort of believe that or go through some stuff to figure it out, but basically that's the deal. So here, if I took the kth root of the top and the bottom here, the top would go to k, the bottom would go to 1, and as k goes to infinity, that goes to infinity. So I would still get this thing to be divergent from the root test. The trick is that I don't have to think about it that way. So here, since I don't have to, it's nice to do the divergence test or the alternating series test or something like that before having to go through and try one of these root tests or ratio tests. So it's always good to try all the tests, the other tests first, and then see how that goes. Okay. Again, I can do this same sort of deal. So how fast does k to the k grow, or k factorial grow, versus how fast does k to the 6th grow? So k to the 6th is way down here. K factorial is way up here. Certainly k factorial grows faster than k to the 6th. So therefore, this is again a divergent sequence because k factorial is the top. It's going to infinity as k goes to infinity. Is again divergent. So these divergent series are pretty nice to spot if you can spot them right away. Again, what I'm applying here, I have to be very careful, is the alternating series test. So the divergence test only applies when the terms inside are all positive. So since we have alternating signs here, I cannot apply the divergence test. I have to apply the alternating series test. And then the alternating series test says if the limit of the inside thing goes to 0, then we're good. It's convergent. If it doesn't, then we're not. That's it. Then we're done. And so I would get that. All right. One final one. So 1 over natural log k plus 1 raised to the k power. So you sort of think about this thing. Divergence test isn't going to be so nice in this situation. Yes, everything is positive, but now I've got to do this limit, and then there's a L'Hopital's rule involved, which is fine, sort of. I would prefer not having to do that, and so I don't actually have to. I can apply one of the tests that we have just done. So the root test says take the kth root of 1 over natural log of k plus 1. All raised to the k power. And then I want the limit as k goes to infinity of that. And I do have to have an absolute value here, but the absolute value of natural log of k plus 1 for k bigger than 1 is just going to be positive. So it won't matter if I put it in there, but I will put it in there just to be complete. So the kth root of the kth power, and the absolute value could drop because it is positive terms there. I've got natural log of k plus 1 in the denominator. K goes to infinity. Natural log of k goes to infinity. I've got a denominator that goes to infinity. So this whole thing goes to 0. And so since this goes to 0, this is a convergent sequence. So it's absolutely convergent and therefore convergent. And so we can conclude this is a convergent sequence. All right. Cool. So that's what I want to sort of end with is a little bit of an example where we can apply this test and it works out. By the way, each individual problem will be sort of individually thought of. So you got to think of it as, on its own. So like for this one, it was easier to use that root test, but maybe the root test isn't as easy as just applying the divergence test. So here the divergence test was going to be hard because we had this limit. It's got a power of a natural log of k. So it's going to be maybe hard to do that with L'Hopital's rule and all that kind of stuff. So here it was easier to actually say, oh, we can actually just say it's convergent by this root test. Okay. One other thing I wanted to mention, so the homework for this week, the last two problems are pretty involved, and so I will not be grading them. They'll just be graded on completion. So try them. I think they're a lot of fun, personally. I really do enjoy those two problems. But I definitely understand that you're all kind of strapped for time, and it's going to be a little tricky. So I wanted to just mention I won't be grading those two, except for on completion. And so I will show them to you now. See what they look like. They're actually pretty cool. So what we're looking at is a fractal. It's Snowflake Island or Koch's Island. So Koch snowflake is sort of part of this thing. And so what you're going to do is you take a triangle, an equilateral triangle. Each of the side lengths is 1. And then I split each of the sides into thirds. The middle third I cut out and put another triangle on. And then I do that again. And then I do that again, and then I do it again, and I do it again. So every single side here is split into thirds, and then I add a triangle inside of that. All right. And so the trick here is to find two sequences. First is the sequence of perimeters of this, and then show that that sequence is divergent. And then you look at the areas, so find the sequence of areas, and then you show that that is convergent. Okay, so the area of each of these is going to be a convergent sequence, and then the perimeter is a divergent sequence. So basically, what this is kind of weird, but it's what it's doing is it's saying the area inside of these islands is staying finite. It's going to some finite number, but the perimeter, the sort of how much I'm going around, how much fence say I need to go around one of these things. Is going to infinity. So the amount of fence that I have to use to enclose a finite area is going to infinity. It's kind of a weird little thing. So again, it's not too bad to figure out each of these sequences, but I do understand that it's going to take you some time to do it. So try them, get something down. I'll grade it on completion rather than on complete on your work. So all right. Cool. So I will see you all later. Let me know when you want to take the test.